Okay, guys, we are doing the dice roll worksheet. You have to roll a dice 300 times. But I'll be nice to you. I will let you roll the dice 6 at a time. So everybody takes 6 dice, and then you're going to roll those 6 dice 5 times. Count the number of 5s, and that is 1 round. So every round is 30 rolls. If you only have 1 dice, I apologize. It's going to take a while. So take 6 dice, roll them all, count the number of 5s, do that 5 rolls, and that is round 1. Okay? So once you have filled out all 10 rounds, then go to the EHS Canvas, find the Google form for dice roll, and then input all your information, and we'll just pause the video. And then once you have all of that done, then I want you to answer questions 1 through 7 on the front page. When everybody has finished that, then I'll restart the video and we'll go over the classroom data. Well, we'll go over 1 through 7 and then the classroom data. Okay, welcome back. So question number 1, how many 5s would you expect in each round? 5. So we suspect that there will be 5 5s because if the dice are fair, then 1 in 6 rolls should be a 5. So if we do 30 rolls, 1/6 of 30 is 5. Now, you'll probably have some that are higher than that and some that are lower than that, but that is the expected amount. And then we find the average. You simply add them all up and divide by 10, and that will give you your average. By raise of hands, how many of you are over 5 in your average? 1, 2, 3, 4, 5, 6, 7. How many of you were below 5? 1, 2, 3, 4, 5, 6, 7. Oh, did anybody get exactly 5? Oh, I thought somebody did. All right. Okay, now standard deviation. So let's say somebody pull out a calculator. I'm going to write down numbers and you give me an average. So let's say I had 6, 4, 7, 3, 5, 5, 6, 5, 6, 6. What's my average? 5.3. So my average is 5.3. So how do I calculate the standard deviation? Well, the formula looks really complicated and it is kind of a mess. But it says take every x sub I, meaning the value for any particular round, and subtract the average. Now, some of these numbers are going to be positive and some of these numbers are going to be negative. Okay? So, what are my differences? So what is my difference here? 0.7. So 6 minus 5.3 is 0.7. Okay? What's my second difference? 1.3, and then 1.7, 2.3. Oh wait, negative, right? Both of those are negative. Okay? And now round 5. So 0.3 or negative 0.3, right? Because it's always value minus average. And then negative 0.3, 0.7, negative 0.3, 0.7, and 0.7. And here is where students make mistakes. In your calculator, if you do negative 1.3 squared, that is not the same thing as the quantity negative 0.3 squared. So according to order of operations, which your calculator follows if it's a scientific calculator, the first one is saying negative 1.3 squared, but exponents come before negatives, so we square the 1.3 and then change its sign. Okay? This is the way you want to type it in. However, the whole point of squaring everything is getting rid of the negatives. So when you calculate standard deviation, I wouldn't even put the negatives in your calculator. Because if you forget and you don't put parentheses around it, then you're actually going to get a standard deviation that's much lower, or in some cases 0, if you don't do that right. So, how am I going to do this without, this is going to be tricky. All right, so I'm going to do 0.7 squared plus 1.3 squared, and notice I just ditched the negative, I don't need it. Plus 1.7 squared plus 2.3 squared plus 0.3 squared, another 0.3 squared, 0.7 squared, and then my last couple of 0.3 and 2.7s. So 0.3 squared, and ooh, don't multiply that. Okay, plus 0.3 squared plus 0.7 squared plus 0.7 squared. Okay, nope, not a 4, a 3, a 7. All right, so that is, so I get 12.1. That is this piece of the equation there. Okay, and now I need to take the average of that, but because this is a sample standard deviation instead of a regular standard deviation, instead of dividing by 10, I'm going to divide by 10 minus 1. So that's where we take the average, so divided by 10, and I get 1.21. Now what? Well, I need to undo all of those squareds that I just did. I squared everything to get rid of the negatives, and then I took the average, and I want the average distance from the average, but this is, I have squared all of the terms initially, so I need to take the square root of the answer, and I get a standard deviation of 1.1. Oh, I'm glad somebody's paying attention. Okay, 12.1 divided by 9, thank you. And now I take the square root of the answer, and I get 1.16. And I'm just going to put, I'm going to do 1.2. So my S, my standard deviation, is 1.2. Okay, what does that number mean? That's the average distance from the average. So if I were to draw the normal curve, okay, it just so happens that the standard deviation is the distance from here to that inflection point, where we switch from concave up to concave down, okay? And 68% of all people should be in that window, right? Okay, so I have an S of 1.2. Oh, hey, great. What should you consider as an ordinary number of 5s in each round? Should we base, my average was 5.3. Should we base the ordinary amount on my average of 5.3 or on the expected value of 5? Off of the expected value, right? We're assuming that the dice are fair. Now, technically, we all should have rolled the same dice, but imagine how long that would have taken, right? Allison gets 300 rolls on one dice, and then Hayden gets 300 rolls. So we're breaking the rules quite a bit. We're sort of testing if all of the dice in the room are fair, and that's really not a very good way to do it. But we're going to break the rules a lot. I'm going to teach you the right way to do it, and then we're going to break the rules all over the place. So we would expect 5 plus or minus my standard deviation of 1.2, or whatever your standard deviation is. So that would be anywhere from 3.8 up to 6.2. Okay? So basically, an ordinary number of 5s would be 4, 5, or 6. So if you're rolling a dice 30 times, and you get a 4 or a 5 or a 6, that's probably going to happen quite a bit. That is a normal number of 5s. Okay? Well, how many of your rounds should you consider ordinary? Oh, of course, I erased mine. So go through and count how many 4s, 5s, and 6s did you have? And I can actually do that. It's just going to take me a second. Okay, so I'm going to circle all my 4, 5s, or 6s. So 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 10, which is 80%. So I actually got more than expected. Okay. What should you consider an unusual number of 5s? Well, something unusual would be 2 SDs or farther. So over here or over here. So I'm going to take my expected value of 5, and I'm going to plus or minus what? 2 copies of 1.2. So 2 copies of 1.2. So that's 5 plus or minus 2.4, which is 2.6 up to 7.4. What percentage of my rolls would I expect to be unusual? So 95 is between 2 and -2. So I would expect 5%. And when I look at mine, I actually don't have any. 100% of mine were within 2 standard deviations. Okay, why is that? Well, I only played 10 rounds. What's 5% of 10? Half of a roll, right? So maybe you got one, maybe you didn't, but 1 is probably as many as you're going to count in that area. Okay, everybody understand that? Garrett, did you figure out your SD problem?
I think so.
Okay. All right, let me pull up the classroom data. So go ahead and turn your paper to the back side. All right, here is the classroom data. Okay, so if I go here, how many rounds were rolled by the whole class? So that's going to be the total number of rolls here, which is 160. So 160 rounds, and remember each round is 30 rolls. Okay. What is the class average for the number of 5s rolled per round? So I'm just going to take the average of that. So equals average of column A. And we get let's just say 5.1 to make it easier. Okay. Do we think the dice are broken? We expected 5 and I didn't get 5. Is that a problem? Gavin says yes. It's pretty close, right? So how close is close enough? Well, we're going to have to draw the histogram, and we're going to have to calculate the standard deviation, and then we're going to have to see how many people are farther away from the standard deviation than what we got, and then we can figure out if we think our dice are fair or not. Okay, so what is the standard deviation? Who wants to volunteer to do that for me? Can you imagine how awful that would be? So we would do 0 minus 5.1 squared plus 0 minus 5.1 squared. And we would have to do that 160 times. Yeah, good luck not making a mistake. So I'm just going to do standard deviation And is this the standard deviation of a population or a sample? Sample. What's the difference between the population formula and the sample formula? The sample formula does n minus 1. That's the only difference. That has the effect of inflating the standard deviation just a little bit. So I want standard deviation of a sample, and I want to do column A. Oh, that's not what I wanted. So this is SD. And I get an SD of 2.24. Okay. Now, what about this person? Who is that? Who is that a 13? Who had 13? Nobody that's here? So, should we throw that 13 out? Well, what are the rules governing whether or not we eliminate a particular round? If you know that there was something wrong with it. Now, apparently whoever submitted that isn't here in class today. But, I mean, if you know that you counted it wrong, then just throw that round out and start over. But if it really happened, if 13 happened, we can't get rid of it. Even though it makes our data really messy. So our standard deviation is 2.24. That's pretty high. But that's just what happened. Why is it standard deviation too high? Well, because of this. We had one count in the 12.3. I like how it didn't make nice even boxes, right? Okay. So, how many 5s are expected in each round? 5. What would we consider an ordinary number? So that would be 5. Oh boy, I better go up to the board. So we would expect 5 plus or minus 2.24, which is 3. Let's make this easy. Let's just say 5.2 or 2.2. So that would be 3.8 up to 7.2. Did I do that right? I like to make mistakes. Oh, so this one actually should go here. Sorry. Okay. Oh, that's what you're freaking out about. 2.8. How did I ever graduate college? 3 different times. I don't know. Why not? So, how many of the class counts should we consider as ordinary? So that's going to be 3s, 4s, 5s, 6s, and 7s. So let's go here. The 3s start at 21, and the 7s end. I'll find it. Maybe. The 7s end at 139, so that's 128. Or 108. Wow. So we had 108 out of 160. What does that give me as a percentage? 0.675. What do you think? What did we expect? 68%. And man, we got 68%. Okay. Going back to this, how many of the class counts should we consider unusual? Well, unusual would be 5 plus or minus 2 standard deviations. Did I mess up again? No, I will. Oh, 118. What does that give me? 0.73. I'm sorry. I can't do math. 73%. We expected 68. We got 73. I was so happy it worked out perfectly, and it was just me making a mistake. Okay, so unusual would be 2 standard deviations. So that's 5 plus or minus 4.4. So that's going to be 0.6 up to 9.4. Did I get that one right? So basically, the unusuals are going to be 0 or anything bigger than 10. So 10, 11, and so on. So we need to go through and count the zeros, the 10s, and the 11s. Go back here. See if I can use this. Oh. So 4 there. And if we go all the way to the top, 4, 5, 6. So 6 out of 160 is 0.037. How many do we expect to be unusual? 5%. 2 standard deviations gives us 95 in the middle, so the edges would be 5. We expected 5% to be unusual. We got 4. Pretty close. Okay. Now, why don't we get exactly the right numbers? Because that curve is not perfectly normal. If that curve was perfectly normal, then our percentages would be better, but the chances of getting a perfectly normal curve are practically 0. So in statistics, we say close enough, and then we move on. Okay. So how many, oh, we already did that one. All right, so we are working with an average of 5.1, and a standard deviation of 2.2. And I'm going to round it to 2.2 just to make our lives easier. Okay, so set up a null hypothesis to test whether or not the dice is fair. So my H naught is going to say the parameter, what is the variable for the parameter? Pi. Pi is equal to the expected value of 5. Now, that is complicated statistician speak to say the dice is fair, right? We expect 5%. So if 5%, or sorry, not 5%, we expect 5 in every round. If we get 5, then the dice are fair, okay? But the alternative hypothesis, H sub A, is going to say pi is greater than 5. Why did I pick greater than? Because my sample average is greater than 5. So it doesn't make sense to set up my alternative as pi is less than 5 because less than 5 didn't happen. Okay? So my sample result helps me choose the alternative hypothesis. Okay? So how many of the, oh, well, I messed it up. We're not testing ours, are we? That's what happens when you make a new worksheet and you don't pay attention. Okay. So let's say you play the game. You roll your 30 dice and you count up the number of 5s and you end up with 4. All right? So the null hypothesis is going to be pi is equal to 5, and the alternative is going to be pi is less than 5. Our 5.1 came from 160 rounds. Okay? So we are just testing one round to see if we should throw that dice away or not. So I give you one dice, you roll it 30 times, you end up with 4 copies of 5. Should we throw that dice away? So How many of the class rounds had 4 or less? Where am I going to get that number? I've got to go to the spreadsheet and count. What am I going to count? I'm going to, well, we're all counting 5s. Which rounds are going to be included in this? 4s and 3s and 2s and 1s and 0s, right? We're counting, so here's my normal curve. 5 is in the middle, right? And I scored a 4. So here is my sample of 4. But in order to do a hypothesis test, we need a p-value. And p-value is the area in the tail. So I'm going to look at my data, and I'm going to count all of these. Does that make sense? So we go to the spreadsheet, and we start with 1. We go down too far. How many 4s are there? Or 4 and lower? 65. So we go over here, and we had 65 people in there. Now what? Well, how many people are on this histogram? 160. So I'm going to take all of the people, 160, and I'm going to count these people, which is 65. So I divide this by 160. What does that give me, Jacob? 0.41. What does that mean? %, of the people in the class had a score of 4 or below. Does that make sense? Okay, now what? So that's my p-value, 41%. So what's our conclusion? We accept H naught. Why? So remember, when P is greater than 5, we accept the null. When P is less than 5, we reject the null. And that's a really weird way to do it. I understand. But that's how statisticians work. Okay? We reject the null. You won't find this interesting or not. Or maybe you will. So on Friday, I went to Utah County and donated blood and ran some errands. Well, I'm O negative, which means I can give blood to anybody. So my blood is like super, super valuable. In fact, if you go to the ER and you need blood right now, and they don't have time to test your blood, they give you O negative, because I am the universal donor. I can give blood to any person. And because of that, they have made it easier for people with O negative blood to donate blood. Instead of going in and donating 1 pint of blood, I go in and they hook me up to a machine, and the machine sucks out 1 pint of blood and then spins it and separates the red blood cells from everything else, and then they pump the everything else back in me. And then they suck out another unit of blood. And then they spin that, and they keep the other unit of red blood cells and pump everything back in me. So essentially, I double donated, except all of the plasma and the platelets, all of that came back. So I only donated 2 units of red blood cells. Well, that was all fine and good, except I got home late that night, and the next morning I went riding dirt bikes on a really, really, really hard trail. And I had no energy at all. Usually when I ride a hard trail, my muscles get tired. Never happened. I just didn't have the energy. Luckily, the guy I was with wasn't super good, so I was able to outride him, even being 2 quarts slow. So I got wondering, how can I build my red blood cells faster. And I wondered, I'm really dumb like this. If I were to hold my breath a bunch, would that rebuild red blood cells better? So I looked it up, and I found a research article, and it said they took these people and they had these people hold their breath until they couldn't, like 5 times, and then they repeated every 10 minutes. Anyway, but I read the abstract, and it said that when you are out of breath, your kidneys freak out because there's not enough oxygen. And so they produce a hormone, and that hormone goes into your bones and tells your bones generate more red blood cells, because your bone marrow, that's where red blood cells come from. So if you want your lungs to be more in shape, you can actually just practice holding your breath and you will develop more red blood cells, I found out. Anyway, I read the abstract, and it said that the people who held their breath during this regimen had 24 times the hormone that produces red blood cells than the people who didn't. And then it said in the abstract, in parentheses, P is less than 0.01. And I got so excited. And I was going to show you, but I forgot to print off the article, so I don't know where it is. But they even reported the p-value. They said p was less than 1%, which means reject the null hypothesis. So the null hypothesis would say the breath holders are the same as the non-breath holders. And the alternative would say the breath holders had more of this hormone than the non-breath holders. Anyway. Yes. So in that case, they would have rejected the null. But in our case, we are going to accept the null hypothesis. Do we feel that our dice is broken? No, we don't. And the fancy way to say that is, there is not enough evidence to suggest that the null hypothesis is wrong. Okay, let's see if I can get this one without making any mistakes. All right. This time you roll a dice 30 times and you end up with 13 fives. What is the null hypothesis? H naught says that pi is equal to 5, the expected value. And the alternative is pi is greater than 5. And I think I got it right this time. Why did I pick greater than 5? Because 13 is greater than 5. Okay. How many of our class counts had 13 fives or more? 1. Out of 160. So Jacob, give me that percentage. Which is 0.6%. Okay? So what do we conclude? We reject the null. Our P was less than 5%, which means we reject the null and we accept the alternative. Okay. What does that tell us about that dice? It's broken. Now, are we 100% sure it's broken? No. Could a perfectly fair dice create 13 fives? Yes. But there is strong evidence, and in this case, it's really strong evidence that the dice is unfair. So we should probably throw that one away or use it against your enemies. Okay? That's how statistics works. And it's crazy that this early in the year we're doing null hypotheses, because that did not exist in any other textbook I've ever seen. And I've seen 5 of them. Yeah. Okay. You guys have everything you need to finish 2.3. So I'm not going to go through 2.3 like we did before because it made everybody fall asleep. So pull out your Chromebooks, do 2.3, and then at the start of class tomorrow, I will discuss anything in there that you found confusing. Okay, hand those in. See you, Garrett.
All righty, see ya.